Yep. Okay, cool. So let's resume directly where we ended in the previous lecture yesterday. So we were looking at fixed points of the beta function, of the beta functions. And then it was useful to linearize your couplings around the fixed point. So you define new couplings that I'm going to call U, such that the beta functions in this U basis as a function of these U's are simple beta U I. So they're diagonal. Let me say, this is in the U basis, the ith component of the beta function. This is in the G basis. And then it depends in principle on all the U's, but in practice only just on a single one at leading order plus order U squared. So these, what we said is that the variation around the fixed points, so G, see, we looked at G star plus delta G, and then we said that the change is just linearly related to these U couplings that diagonalize the beta functions. So note that these couple, of course, in the couplings in the Lagrangian then look like this, sum over I delta Gi integral d dx. So I'm omitting powers of lambda here, but you can insert them yourself, or you just absorb them in the definition of these operators. So if we just make this simple substitution, then you see that the ui's couple to some combination of operators, which is basically given by x times the original operators, or some uj sum over I. Basically the transpose of x, oi xij. So these are new operators that I'm going to call OJ. And these are, of course, nice because at least at leading order, the beta functions have this simple linear form, so these operators also scale homogeneously. So we're going to call those the scaling operators. And so they're basically the operators that diagonalize the beta functions. Yes?
So these are the directions of the flow.
The beta functions define the flow, right? So yeah, the flow, so it's like if you have some fixed point and it looks a bit like this in G space, then of course the U variables are just like the tangents of the attractor of the well, the unstable manifold and the stable manifold, as they're called in dynamical systems language. Yes. Okay, any more questions? Yes?
Are all the stable points instants when you confine a CFT, or only some of them are proper places to start to look for conformal theory?
They are all scale invariant theories by logic that I want to explain in the next 5 minutes. Whether scale invariant theories are conformal invariants, are conformally invariant theories, that's logic I want to explain in the next 30 minutes. So the claim, of course, is that there is scaling, there are lots of power laws at these fixed points. So for example, at the level of correlation functions, your Cullen-Semantic equation basically reduces. So let's look at two of these scaling operators for simplicity. So you have to do very little work to see that this Cullen-Semantic equation at the fixed points, well, this definitely goes to 0. And then there's the scaling of these operators, which induces, because of this delta tilde minus d, and the relation between the scaling dimension of the operator and the first derivative here of the beta function. And then because there is a ddx here, so these have canonical dimension d. So you work a little bit and then you change the lambda, dd lambda with an x ddx. And if you do all of this carefully, you will find that it's these deltas that remain. So I gave them a tilde here already because they're not the engineering dimension of the operator that you have in the UV fixed point that determines how many powers of lambda you are expecting. The lambdas are all absorbed in the operators here, so we don't bother about lambda anymore. We're just looking at the dimension as it appears as the eigenvalue of the linearized first derivative of the beta function. And that eigenvalue is what appears here. And again, I mean, if you want to be careful and see where they come from in the UV, you would have to insert all the lambdas here, but in the end, you'll find the same equation. So my claim is that the Cullen-Semantic equation then reduces to this, which is, of course, a homogeneity equation. It's very easy to solve. It shows that u tilde I of x, O tilde I of x, O tilde j of 0 is just some constant divided by x to the power delta I plus delta j tilde tilde. So this constant can depend on the operators, C, I, J. So we see a simple power law, and that's what my claim was, they're power laws. There's one. Right, so scale invariance means power laws to some extent. It's, right, this thing is not, it's not like you scale it and it stays constant, scale it and it transforms homogeneously. That's the rule of scale invariance. Yeah, I used a lot here. It is, yeah. Right, so what should we say? Well, I used translation, it was built in from the beginning. Even rotation, the symmetry was built in my cutoff with momentum space cutoff. So we suppose here, so translations, and rotations are symmetries. Of course, it's fairly natural if you start with some lattice system that translational symmetry emerges in the continuum limit. Rotational symmetry is maybe a little less obvious, but it appears because from the field theory perspective, the underlying lattice will give rise to operators that preserve lattice symmetry but break rotations. So you can ask, well, what's the first operator? What's the kind of operator that preserves lattice symmetry and breaks rotations? Does anybody have an idea? If you start for the square lattice, for example, and you do phi to the fourth theory, so just have a scalar field, and you break rotation symmetry. What's a good thing? That's not a total derivative. I could think of one. So maybe this is a comment. So you can do something like, I'm not even sure this works for a real scalar, but okay, let's see. So you can do phi the x, well, you can try something like phi dx squared phi, for example. Phi dx phi would be total derivative. This you can rewrite you can rewrite so that it's not fully a total derivative. You can do phi dy squared phi plus phi dz squared phi. Let's say I have a three-dimensional lattice, right? This looks a bit like, okay, I have x and y and z, and those are sort of my three lattice directions. And so I can write something like this that would maybe give, like, have some lattice symmetry, but not much else. But this, of course, is also just a Laplacian. And so as it happens, it's just rotationally symmetric. So I think something that you can do is something like this, dx to the fourth, dy to the fourth, dz to the fourth. This is something, at least with a complex scalar, it works. I think with a real scalar, it's also not. So this would be an operator. I think it's also not a total derivative. And so this, it would be an operator that would preserve lattice symmetry, x, y, z. You have these three rigid axes, but is not writable as something that is rotationally invariant. But you see this operator has this engineering dimension of delta phi, which is d minus, so that's 1/2 in 3 dimensions. So it's 1/2 1 plus 4 derivatives. So the dimension of this operator is, so let me do it like this, 5, which is way bigger than 3. So this operator is hugely irrelevant. Now, it might be that it's dangerously irrelevant and that at the fixed point, it becomes suddenly relevant and then you would have to tune it. And so then you would have to be very careful. And generally, you would not see rotational invariance coming. But 5 is a long way from 3. So it's very unlikely that this operator comes all the way down and destroys your rotational invariance at long distances. And that's, of course, what happens in practice. We know that you can put this model on a lattice, you can simulate it, and then you will find approximate rotational invariance in the continuum limit. So this operator does not appear to be dangerously irrelevant.
Still, the operator is kind of eigenvectors in some sense of other operators related to the G that are eigenvectors of the fixed point.
Sorry, these O tildes, what was your question about?
I was wondering if there was one related to the eigenvectors G of a fixed point, or?
Yes, yeah, like here with the same x, right? This x is this x, the diagonal axis. Yeah. That had nothing to do with rotational variance, right? This was just, okay. So that's a comment about rotational variance. So generically, because these operators tend to be so big and so irrelevant, generically they're washed out and their effect goes to 0 at long distances. So yes, that's why I assume rotation with this caveat, and translation is sort of what you're supposed to get in the continuum limit anyway. So correlators were one thing. Another thing that, of course, has power laws are all the sort of equilibrium observables. So in the language of field theory, those would be the derivatives of the partition function, or more precisely, its log. Like you get all kinds of susceptibilities and so on. Magnetizations, specific heat, all of these things. So more precisely, let's define something log z over v, where v is some abstract volume, which is the free energy density, roughly speaking. So in this language, the free energy has units, engineering units of d. So with a cut of lambda, if only scale in the game, then it should be just lambda to the d, otherwise you will not get a free energy. F tilde, which can then depend on the dimensionless couplings. Now let's apply a Kalan-Zemantic type equation to this. So we go near the fixed points. So we go to, so near the fixed point, we do again this linearization game. And we transform the G's to the U's. The Kalan-Zemantic equation becomes, roughly speaking, this. So you get a D from this. And now this thing depends on the couplings U. Plus sum over delta minus D. UI, just the beta functions, d ui, f lambda. And I'm going to say that this is 0. It's not quite 0 because the log of the partition function, and the partition function under like the measure in the partition function may also change under this change in your coupling. And so if the measure in your partition function changes, then this gets an additive constant. And so this is actually not quite a 0. There's an inhomogeneous piece in the Kalan-Zemantic equation for the free energy. But that inhomogeneous piece does not affect what I'm going to say next about the power law scaling. The leading power laws come from this piece. And all the extra bits that you get from the inhomogeneous bits don't matter. So this is not really true. But you can find lots of lecture notes where the unimportance of this inhomogeneous bit is explained. One particularly nice book that I like is Hardy's. Is by Jack Hardy, which is called Renormalization and Scaling in Statistical Physics, I think, something like that. And I think Denis also has some excellent lecture notes where you can find these kind of details on his website. It's again for and by amateurs, but I'm not sure if I agree with the amateur classification there. Anyway, so this is the Kalan-Zemantic up to this inhomogeneous piece. This is the main driving force for the scaling behavior of the free energy. Because what you're going to get is you can try to solve this equation again, and I'll leave this as a first year calculus exercise. You'll find that f lambda of these ui's is just u1 to some power d minus delta 1. So that'll take care of this d piece, and then some combinations of the other u's, u2 over u1 to the d minus delta 2 over d minus delta 1. u3 over u1 to the power d minus delta 3 over d minus delta 1. And so on. Yes?
Be sure the first D in your last line on the left is not a difference, it's the dimension.
Yes. Yeah, it's the same D. And it's all the D's. Yes, so what you find is that you can solve this equation. It tells you how the coupling dependence must be. You can solve it in terms of like so. So you say that it can only depend of strange power law, strange combinations of the U's with some funky powers. So my claim is that this solves for any phi, capital phi, this solves this equation. And I'll leave it to you to verify that. And then, of course, you get the power laws from this, right? So, for example, if you do Ising, or in my book, lambda phi fourth, by universality, they go to the same fixed point, then we basically have two relevant operators. One of them I talked about, which is the operator, like we can roughly speaking identify it with phi squared. We call that phi to the fourth becomes irrelevant. So we say this is phi squared up to, of course, an infinite sequence of quantum corrections. On the lattice, it would be the energy density, also denoted as epsilon. And what we identified with physically would be the temperature. So we'll call this, instead of using U1, I'll call it T. And you can think of it as a dimensionless version of T minus Tc. But there's in fact another relevant operator that we did not talk about, which is just phi itself. It's also sigma or S in the Ising model. And I can call it H for some I'll call it H because its source or its coupling is basically the external magnetic field. So in Ising, there are two relevant operators, and then there are all the irrelevant operators, but at the fixed point, they don't matter too much. So then you get that F lambda of T and H, and all your irrelevant operators is T to the power D over D minus delta epsilon, right? I'm just substituting. Delta 1 is delta epsilon, and delta 2 is delta sigma, and U1 is T. So it's just rewriting phi to the power U2, well, H over T to the D minus delta sigma over D minus delta epsilon, and then all your irrelevant operators. And from this, you get all your critical exponents with almost no extra work. Right, let me just write one, the specific heat, the second derivative. How does it behave as t goes to 0? Well, you take two derivatives, you get some extra stuff, but in the end, you just set you set h to 0. And so what you get is that this behaves like t to the power minus 2 plus d over d minus delta epsilon. So this is, of course, equal to t to the minus alpha by definition, where alpha is one of your critical exponents. So you get your critical exponent alpha in terms of the scaling dimension delta of this scaling operator. And similarly, you can get all the other critical exponents in terms of delta epsilon and delta sigma, or at least the leading few. And then the corrections to scaling will come from the irrelevant operators here, which will introduce new deltas. Yes? All the deltas should have tildes, and I'm gradually dropping them. Because in the end, I want to talk about conformal field theories. Let me drop them in a less gradual manner. So then everything is a little bit more coherent. Yes? Yeah? Oh, this is one thing. This is a specific heat. You can take the first H derivative and get some kind of magnetization, depending on whether you do it at external at H equals 0, or it's spontaneous magnetization, or the forced magnetization. You can get susceptibilities, right? All these things follow from, they're just the derivatives of your free energy. So my point here is not to give you a full classification of all the critical exponents and tell you how things blow up and what alpha, beta, gamma, delta, eta. I just want to tell you that these critical exponents, the leading ones, are just determined by two numbers, delta sigma and delta epsilon. And so we want to know really these scaling dimensions, because these are things we can in principle measure. People do measure these things, for example, for the O2 model, for superfluid helium. It was famously measured So at the critical point, they thought the effects of gravity were too strong, so they moved the whole experiment into space. And so famously, some critical exponents have been measured on the space shuttle in the 90s or 80s, late 80s, I forgot. So they are some of these are known quite precisely. And of course, you can measure them on the lattice fairly easily as well. So we would like to know, and this is the upshot towards the next step of this lecture series, which is we want to know what delta sigma and delta epsilon are. Okay. We want to know a lot more, of course, but those are really the most important targets. What I've not talked about, and I can talk a little bit about it while I raise this board, is that there are corrections to scaling from the irrelevant operators. There's the inhomogeneity of the free energy, which is important. There are analytic corrections to this, which are important. There are universal amplitude ratios. There's finite size scaling. There are all kinds of things that you can discuss about this critical. But I really don't want to give a lecture about that. I want to move on and discuss conformal field theories. Okay? Good. So what's the CFT? We haven't quite answered the question, but I'm gonna get there. So CFT, this is part 2, CFT axioms. So a CFT in some, yeah, let me say that this is a reasonable definition. A conformal field theory is a quantum field theory with invariance under, so we have the translations and rotations on which I made a comment just a few minutes, rotations, but then we of course have scale transformations or dilations or dilatations. Let me just write scaling. So these are, of course, are all implemented by vector fields. Dilatation, there's only one, x mu d mu. And, sorry, rotations, what am I? Oh, I'm off by one, sorry. And then a conformal field theory has one more set of symmetry, which are special conformal transformations. Which corresponds to a strange set of vector fields 2 times x mu d mu minus x squared d mu. So where these? Who ordered these, right? So CFT is a question now. If you believe everything, it's a question like those guys were obvious. Translations, rotations come in the continuum limit. Scaling becomes a question of tuning your beta functions, but we only had a few relevant operators. But so with a bit of tuning, we get scaling. But then why special conformal transformations? So our question why CFTs is now a question why this? And frankly, the answer is still not as complete to this question as I'd like it to be. Oh, I have a new board. But there are some words that people say, and I'm going to say the same words, and then you can be. And then I'm going to say a little bit about what's not so great about these words. I think you'll find it yourself. You'll see for yourself why these words don't give you a complete answer. So of course these vector fields, they have commutators, and so right, you can do this as an exercise. So rotations and translations, well, that's just Poincare algebra. do something like this, and then you find all the non-zero commutators, or you ask like your sister in high school to do this because it's all very easy. K nu is minus K nu, and K mu P nu. This one I'd like to write down, delta mu nu D minus 2. D is same as is always your space-time D. This forms an algebra, and the algebra is SO. Does anybody know? Right? SO. In D plus 1, 1. D plus 1, 1. The Euclidean conformal algebra is SO D, 1. So D plus 1, 1. Let me write small SO, because it's the algebra that we're talking about. The group is a more complicated beast because you have to exponentiate these things. You have to decide whether you include parity and so on. So I'd like to stick to the algebra most of the time. So I have to write small SO. So small. I think in the literature you will. It's sometimes a bit confusing. You have to be careful about what the group is. So often, especially if you go to Lorentzian signature, you want, for example, not SO. So in Lorentzian signature, you don't get, well, you get SOD, 2, and be the algebra. But what's really the group is probably some universal cover of this, and not just SOD, 2 in itself. So in D equals 2, you get SO2, 2, or say D equals 2, you get SO2, 2, which is basically 2 copies of SO2, 1, but the group is more like universal cover of SO2, 1 rather than just SO2, 1. So stick to the algebra is my advice. So I need to introduce standard CFD concepts, and I'll try to be reasonably efficient. But some of you will probably have seen this. So a partial answer to this why question, so if this is the question, then a first step towards the answer is that special conformal transformations are a symmetry if you have a stress tensor, and the stress tensor has 0 trace. Not quite 0, so I'm writing a tilde now. It's 0 up to contact terms in flat space. So if there exists a stress tensor now, why would a stress tensor exist? That is a separate question entirely. This is part of where the answer becomes a little bit unsatisfactory. So in quantum field theory, if you start with the field, you see the stress tensor as just the coupling, the response of the theory with respect to a change in the metric. So you can just write T mu nu, you make your theory couplable to curve space, you take the derivative of the action with respect to the inverse metric, and you stick some factors in there. This is a way to, right? So if you have a quantum field theory, you have a Lagrangian, you differentiate it with respect to you generalize the Lagrangian to curve space theory, you differentiate with respect to the metric, you get the stress tensor. This is an operator. This works. So in local quantum field theory, it's kind of fine, but what if you start with some lattice model and you go to the continuum limit? It's not entirely clear. There's some arguments as to why a stress tensor should appear, but it's not super clean, I think. I believe the arguments, but you should, for example, in Cardy's book, but you should read them yourself if you want to know more about this question. Yeah.
In the algebra, you didn't write the remaining
No, I wrote dot dot.
Because they're zero or because they
No, there's some commutators that are, yeah, ask your sister. That's fine. Yeah? No, it's 0 up to contact terms in correlation functions. Okay? So it's 0 away from contact terms. Only, so, I should say is 0. So 0. So this is not really like a standard scaling operator, right? It's not nice power laws. It's just some operator that's almost everywhere 0. But if you touch another operator, then you get something. You get some delta functions, maybe derivative of delta functions. So okay, in quantum field theory, we have this, but it sounds a little exotic. Sometimes there are crazy quantum field theories where we don't have an action. We just exist. This is really just idiosyncrasy. This is my own background. But there exist funny quantum field theories like in 6 dimensions, which have no, but like anything you can measure, but this comes out of string theory. There exist quantum field theories where we cannot write them, the partition function, as the integral over some fields with some action. Not as far as we know. They come from some string theory constructions, for example. You say low energy limit should be a quantum field theory. And this quantum field theory is local and this is just, it's a thing that's, it's very, you can see that it's all consistent. This theory is local, it has a stress tensor. So maybe the existence of a stress tensor should not be taken from some kind of microscopic definition, but just as a definition of what it means for a theory to be local. Who knows? So already the existence of a stress tensor is something worth discussing. So, so there exist exotic theories, also in 4 dimensions, by the way, but they're all supersymmetric without a known S. Also, what about emergence of T from lattice descriptions? I mean, you can make some argument there. It's not a completely unknown thing, but I'm not going to discuss it. It's subtle, is what I want to say. And lastly, what about in particular about long-range models, where so we say the stress tensor is a mark of locality, but long-range models are not local. They don't have a stress tensor, not as a local operator in any case. But long-range models do seem to become conformal at their critical point. So long-range models, there's some coupling. You can think of Isings, but then where the interaction is not just nearest neighbor, but falls up like with the power law. Everything talks to everything, but there's a power law follow. You can tune this coupling to a critical point, and at the critical point, it's conformal invariance. Why is there conformal invariance? Well, this argument doesn't work, so you have to come up with something better. Now, perturbatively, because there's some kind of Wilson-Fisher type description of these things, perturbatively we understand it nowadays a little bit better, but it's not so. It's not as easy as just saying that there is a traceless stress tensor. And non-perturbatively, I think there's no argument. So the question is still a little bit, why CFTs? Well, here's the partial answer. If you assume that there's stress tensor exists and it's traceless. So now let's zoom in a little bit on the theories where we believe that the somehow comes out of the description. Let's see why it would be traceless. y straight would be 0. Unless there are questions about qualitative discussion. I was here. So now we have this stress tensor, and it should somehow do for us a lot of things. It should implement the translations and the rotations, and by assumption also the scaling. So recall is just like a quick way to say that it's like proof by intimidation, right? You're supposed to know this. So I can give you offline a better argument for why this is true. But the stress tensor is supposed to implement for you, in particular, translations. So this gadget should reduce to O1 to x1. The nu OI xi. So what I'm doing is that these are the classical symmetries. There is a quantum generator of these symmetries, which is essentially the stress tensor. And this is the action of the quantum operator p nu on the operator O of x. Okay? And that's what the stress tensor does. So indeed, this gives you translation invariance because, and this is for scalars actually. If these operators are vectors, something else entirely happens. There's a new term, and if they're tensors, similarly. But this is for scalars. I know a break should be happening soon, but give me a few more minutes. So why does this lead to translation invariance? What's the argument? Recall. Yeah, but I mean, I don't see translation invariance. What's the symmetry? What do I need to get? I need to get somehow that if I move all the operators a little bit to the right, then it's fine, right? So I want to get like this, but then without the delta function, and I want to get it to be 0. Because if I have sum without the delta function, and then I say that that is 0, then I have moved every operator a little bit. That's the first order effect of a translation. So what do I do to get rid of a delta function? Well, I just integrate. Over y. So, and I integrate everywhere. And then this is a total derivative. So by integration by parts, whatever, it's not integration by parts or just by Stokes' theorem is what I should say. It becomes an integral over, well, I integrate, it becomes something localized on the boundary of my integration region. But I can pick this, I mean, this is a delta function, as long as my integration region covers all the xi, I have what I want. But let me take this integration region h, so that this thing becomes an integral over the stress tensor over some region that is very, very far away. And then I say, well, if the stress tensor is very far away, then it doesn't matter anymore, because then I use cluster decomposition. Which says that T mu nu, well, dot, 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 for anything that remains finite as y goes to 0, basically becomes a product of a 1-point function of t mu nu of y, and then dot, dot, dot. But the one-point function of a tensor by rotational symmetry and translational symmetry should just be 0. So this is 0. This is as y goes to infinity, not as y goes to. So so I snuck in another axiom here, which is cluster decomposition, which is again some idea of locality, due to some idea of locality. But if I assume all that, then I get that what I want, I get sum over I O1 xn p nu O I xi equals 0. And then I have my translation word identity. So this is how the stress tensor is supposed to be responsible for the implementation of these of this translation symmetry. If it's defined in a finite domain, then in principle you might not have translation invariance, because we're in a finite box. If I'm here, I'm 2 meters from the wall, and here I'm 1 meter from the wall. But if my box is periodic, then I have boundary. Then I have translation invariance. So if my box is periodic, then again there's no boundary, and then it disappears, because I can just integrate over the entire box. Or if my box is a sphere or whatever. If there is no boundary, then it's fine. But yeah, on space with a boundary, you will not have every translation invariant. Yes?
Just to clarify, the translation invariance comes just from the existence of T, right? Not from any property.
It's the fact that there exists an operator that does this for you, right? The T should be an operator. Divergence is easy. This is a property of T. The existence of an operator that does this, yes. So note that to make all of this compatible, the dimension of T should be D. So what about rotations? Well, the same works for rotations. But you would have to implement, for tensors it's a little bit more subtle because there are derivatives of delta functions appearing on the right-hand side, so things are a bit more complicated. But for rotations, you can use the same trick, which is box mu, p mu nu, x rho minus t mu rho x nu. So this is the thing that you're supposed to, well, let me write it y. This is now the thing that you are supposed to insert, and you do the same trick and you find rotational invariance of your. Okay. And the reason that this is 0 away from contact points is that this is, of course, sorry, minus t, well, t mu rho y nu. So this is equal to, and then we have delta mu. So t rho nu minus t mu rho. So you see that this is 0 away from contact points. This is 0 from contact points, and my stress tensor is symmetric, at least away from contact points. And so this away from contact points is 0. So you just insert, you use this, and then for scalar operators, this is the right rule. You'll find rotational symmetry of your coordinate. So I'll leave this as an exercise. And the last one that I want to mention before the break is scalings or dilatations. We'll try something like Well, we want the dilatation action on this operator. So we just have to contract this, right? D on an operator should be what? Well, it should implement the rescalings of the positions. So it should be x mu d mu of the operator. But it's not just that, right? We had from the Kalan-Zemantic equation, we see that the correct expression is where this operator also scales with its dimension, its scaling dimension. And now I dropped the tildes. So from now on, neither on, well, I should have said it earlier, on the operators, they're already gone, and also on the deltas. So this should be for operators on this. So this x mu d mu we can kind of get. We had the d mu already, so we'll just throw in an extra x mu. So we'll try this. D mu nu x nu. Which is, of course, d mu nu plus times x nu plus d mu x nu delta mu nu, which is d mu nu. So now we see the trace of the stress tensor as an important ingredient. And so it would be great if this were also zero away from contact points. Because that would be one way to implement scalings. But of course, it's not strictly necessary. So one thing I want to, let me see what I want to give you as a break. So we need to break. So we need to know d mu mu of y. So let's just restrict ourselves to scalars again. So we need this to have a form to get rid of, to implement this delta, right? So of course the form should be like, if it's just this delta times the Dirac delta functions, then it'll work. But there are also make it, which can still make it work. So I don't want to spoil them, but think a little bit about what this could possibly be so that you get this scale-wide identity in the next 5 or 10 minutes. That's the break. How long shall we take? Sorry, 10? 10, okay. So you have 10 minutes to think about what this can be. And I'll give you some general answer in the next session. Thanks.
Just to check
now,
that,
now I'm on.
it's on.
So let's try something like this as our current for scale symmetry. So what we're going to get is, of course, if the derivative hits the stress tensor, then we get what we had before, but with an extra factor inserted, because this y mu multiplies it. And if the derivative hits the y, we get the trace of the stress tensor. But of course, we know that d of O should be x mu d mu O plus delta O, as I wrote down. So we need an extra delta, and that better come from here. So, and then of course we get scale invariance, but let's recall the scale invariance comes from integration, what did I say, Stokes and cluster decomposition and integrate. And all of that, so integrate, Stokes theorem, cluster decomposition will then give you the dilatation. Or scale Ward identity. So the fact that if you apply this D operation, all the operators, then your correlation function is invariant. That's the Collins-Semantic type equation we saw before. So we need that if we integrate this, so the integral d dy of t mu mu of y O1 to On should give us what we need, which is delta I sum over I delta I O1 to On. Right, then we're happy. So we need, so we can say, well, t mu mu of y should be something like delta d of y minus x I, well, sorry. So t mu mu O1 to On should be something like delta functions, delta I sum over I O1 to On. So this would do the job. Well, the logic doesn't quite work in this way. The logic works in this way. But of course, there's more that can happen, right? So there are various other things you can try. What else could happen? Can you think of something else that's right? This will do the job, but what if there's something else? What else could there be? Well, we're supposed to integrate this, right? Over y to get what we want. Integrate and use Stokes. So a total derivative. Yeah, sure, why not? If it would be d mu j mu of y O1 x1 to On xn. That would also work. Why not? Right? So this is a problem because, well, okay, I'll come to the problem later. So let me first say that if the stress tensor is not quite zero away from contact points, this J can be just your regular operator. It can just be zero away from contact points. So J mu is just in the list of operators. If it exists, then it's called a virial current. So note that the scaling dimension of this J, of this virial current, should be d minus 1, because its derivative should be give you something of d, of dimension d. So now we're just going to wave our hands a little bit and say that, well, two things can happen. So first of all, the quick argument is just to say generically there's no reason that such a virial current should just pop up in your list of operators. These deltas are just some, these deltas, the dimensions of these operators are just the eigenvalues of this linearized flow equation. So you linearize the beta functions around their fixed points. You get some deltas, they're just some complicated numbers. They're most likely, in most theories, they're in 3 dimensions in particular, they're not rational. It's very unlikely that you get exactly a current vector operator with this dimension. The stress tensor is a special case, right? It generates all these symmetries, it's there by locality, it's the derivative of a dimensionless action with respect to a metric. And if you do it more carefully, you're gonna see exactly that it has the dimension d. So, so the stress tensor by construction has dimension d, but this is just some guy that pops up. So we say that generically it does not exist. There are also more comprehensive arguments. So for example, in d equals 2, if you find such a virial current, you can play some game. This was shown by Zamolodchikov a long time ago. You can play some games and absorb it in a redefinition of the stress tensor. So in d equals 2, it definitely, it's not really a thing. You just change your definitions a little bit and poof, it's gone. In d equals 4, there's some similar arguments that these virial currents should not exist. In particular, Zohar Komigotsky looked a lot at this, and with some additional arguments, you can make a good case that this virtual current should not exist in 4 dimensions. This virial current should not exist in 4 dimensions. And in d equals 3, I think it's wide open. Oh, and the arguments that I cited in 4D, they rely crucially on reflection positivity or unitarity. So if you have a non-unitary theory, then indeed a virial current may exist. There are some simple examples where a virial current exists.
Using the amelioration, isn't it possible to take the virial current inside of a validation of a TMU even in high dimension?
It's not always possible, no. I mean, there's some exceptional cases like free theories or so where you can shift things around a bit, but most of the time it's not possible. That's when J mu is itself like a derivative or something like that. But these redefinitions is not something I wanted to get into. So generically, it does not exist, but then, so I'm continuing that sentence. There's a little bonus, because we can look at this guy, and we multiply it with 2y nu y rho minus y squared delta. What is this? Well, it is derivative hitting the stress tensor, so it's d mu t mu nu plus 2. Well, you can work out a little bit, and what you'll find is that this, with again very little work, is proportional to the stress tensor times the trace of the stress tensor times the y rho. And so if the stress tensor would be total derivative, like this, then in the correlation function, you would integrate it by parts, and you would hit the y. You would get something non-zero. You would just get the j back. But if the trace of the stress tensor would be 0 away from contact terms, then this is an extra symmetry that you get. So this is an extra symmetry. So what should I say? If t mu mu is 0 away from contact points. And this symmetry, this is of course the killing vector, the conformal killing vector field associated to the special conformal transformations that I wrote before. So these extra symmetries, they're labeled by an index rho, and these are your special conformal transformations. So the existence of a virial current, the non-existence of a virial current implies that you get this bonus symmetry. And so that's why, so this is the bonus symmetry. It generically does not exist. So in some sense, that's the best argument we have, apart from some special cases, that's the best argument why it's conformal field theories. Like I said, in 2 dimensions, you can get rid of it in I think all cases, or definitely in unitary cases, and in 4 dimensions, it's plausible. And more generally, it's just unlikely. So for Ising, for example, people can try, if you want to rigorously show that Ising in the continuum limit, say in d equals 3, produces something conformally invariant, what you have to track is the dimension of this J mu. One particularly nice thing you can try to do is to look at the Ising system, and maybe this vector operator, its dimension is bounded from below and it's above d minus 1. It would be great if you could show something like that, because then you would rigorously show that Ising would be conformal in the continuum limit.
What you write on your left quote, does it mean that this extra symmetry does not exist if we are if T mu is non-zero, or
if T mu mu is J mu, if it's non-zero, well, we still have scale symmetry, so this is what T mu mu can be. If T mu mu has this d mu J mu in it, then indeed the symmetry does not exist, because this, what happens is that you're supposed to integrate this, but if you want to implement this operation, you integrate T mu mu multiplied with y rho. So you have an extra y rho sitting here that you're supposed to integrate, but this y rho is going to be hit by, if you're integrated, this is no longer a total derivative. This d mu hits the y rho by integrating by parts, and you get just the integral of j over all of space. And j is, if it exists, it's by assumption not zero away from contact points, so you just get some complicated integral of a correlator. There's no way that this is zero.
What about if you have some extra symmetry and you have some conserved conversion associated? Couldn't you add that term also?
But if it's conserved, then it's zero. Then it's zero away from contact. So this J mu, when I say it exists as an operator away from contact points. So this is what we see in simple systems. There is no virial current, so likely, like there's no virial current, so we get this bonus symmetry. But again, it does not cover theories where there is no stress tensor. It does not cover quite theories where, like long-range models. It does not quite. It's not completely satisfactory because it relies on some sort of accident or so the non-happening of a certain accident, right? It could be, there could be just some accidental virial current and then you're screwed. So there's simple models, like non-unitary models of elasticity and so on, where it's a free theory, and in free fields, you get simple scaling dimensions, and you can construct something like that. There's one more term. There's a mystery term, which we could add something else. So suppose the virial current does not exist, but there's still something we can do. And this is not for generic operators, but it is for certain operators. I want to show that. Oh, I can show everything at once. And this question mark is actually very important. We should have mentioned it at the very beginning. Like this whole virial current is a bit of a distraction. It just is explains why we have CFTs, but even if there's no virial current, then there's definitely, for many operators, there's some extra bit here that we should discuss. So what would that be? There's no virial current, so this thing is completely, this thing is completely gone. It's zero. The stress tensor is therefore zero. The trace of the stress tensor is therefore zero away from contact points, but on contact points we could still get something. So we could try something. So we already have the delta function. So what about the derivative of a delta function? With some number, maybe. So would this work? Well, xi sorry. So could this be a thing? Could it appear? Well, there are lots of problems with it, right? What is an obvious problem? There are two obvious problems. It integrates to zero, right? It wouldn't modify anything. So what's the problem? The index, yeah, there's an index. What about this index? It wasn't there before, so it's not covariant. There's another problem, which is the scaling dimension, right? I've added 1 to the scaling dimension because I've taken one derivative. So, but we can get rid of it if this operator, well, this operator are by assumption scalars, because if we weren't looking at scalars, there would have been already with rotations way back, there would be a problem. So we would have to have some extra contact terms. So this operator does not carry an index, but one thing could happen. We could say that if operator I is, suppose it is the derivative of another operator, then I can free up an index. I can move the derivative to the other side. So then I could say, maybe this can happen. You see, now it works out. The indices are contracted and the dimensions are also fine. And so for operator, and this is actually what happens. There's a number there, and that number you can is not zero. So this would be strange because the transformation properties of the operator under this special conformal transformation are then what? So k mu on an operator. Well, what did we have? We had this vector field xi. So it's definitely it's a 2-index guy, right? Xi rho nu. So xi mu nu. Am I doing this correctly? D nu. I think it's that. Yes. Then we had from the extra contact term, from this, we had T mu mu. Where did we have it? T mu mu times y. Right, so we have y mu times T mu mu, and the T mu mu just gives me a delta function. So that's y mu times delta. And if I'm precise, there's a factor 2. I think I missed a factor 2 here. Let me do it in red because it's my mistake. So I think this factor 2 shows up there. So this would be one way. that we get from all this construction. But if you have this extra term, the nu a nu of x, well, I can also write this as p nu, because the derivative is just the same as p. Then we get all this stuff on p nu a nu of x, plus my extra term, which will be, where did I write it? X mu, so this stuff is an index mu, x mu a. Sorry, it's, what am I doing? A mu, yes, a. Mu of x. Because there's an extra derivative and an extra y, so by integration by parts, you're gonna get the derivative hitting the y is going to give you a d, so you get an extra d, and then this number is the same as that number.
The relation between k and xi, is that a definition?
Yes, xi is this thing. It's just what is called a conformal killing vector field. It's the same as saying that d on O was x nu d nu plus delta times O, right? That's the implementation of the dilatations. The implementation of the special conformal transformation is acting with the killing vector field and then doing this extra little rescaling. So this is the quantum operation that corresponds to this symmetry, this vector field, which is called a conformal killing vector field. Right, I wrote a bunch of vector fields. This is the same vector field. And so the vector fields are just, so for every vector field, P mu O, there's always the action of the vector field on the operator. That is like the transition from the classical symmetries to the quantum symmetries. There's always the vector field acting on the operator, and then there could be some other stuff. For example, for rotations, of course, it's just x mu d nu plus minus x nu d mu. So that's the rotation acting on the operator, if it's a scalar. But of course, if this operator has some kind of index, then that would also be the corresponding rotation matrix for this index, which would also act on the operator. So there's the classical vector field, and then there's the quantum version of how these guys act on operators. And so for the special conformal transformation, I just wrote it out. So this is the vector field acting on the operator, and this is the extra little bit that you get in the quantum version.
Why do you say quantum? I mean, also classical things.
Sure.
Also classical things can have been.
Yeah, fine. Let's replace quantum with field theoretic. The field theoretic implementation of these symmetries. Yeah, very good. Yeah.
What do you make with the last line with the two years and
Oh, there's a plus. There should be a plus. Plus 2 times this number. This is a number, and this is the same number. I don't know what the number is at this stage. Actually, I didn't even bother computing the number, and we're not going to do it here. How could you check that this number, is there some consistency condition? This is bootstrapping, right? Like from first principles. Like you don't compute it explicitly, just try to think of a consistency condition that gives you this number. What's a good way? We have everything, right? We know in principle how rotations and dilatations and all of that acts on A's. What do these generators have to obey? commutation relations, right? So we'll just compute P nu K mu on A nu of X, and then we subtract these two, and that's a commutator. And then we, the commutator is something, I wrote it down, it's like dilatations and also rotations. Now it's a bit subtle because this A is now a vector field, is a vector valued operator. So there are some extra matrices appearing here and there. But in principle, this is how you can determine this particular number. By demanding that the commutators do whatever they're supposed to do. In practice, I didn't bother because I don't particularly care. So taking a step back then, things are fairly complicated when it comes to the conformal algebra and their action, their quantum action, I want to say, but I'm now going to say their action in field theoretic terms. Things are a little bit complicated if the operators are derivative of other operators. So let me make my life simple and say primary operators are not derivatives of other operators. I mean, it's a bit more subtle than that. More precisely, I want to say that there's no extra term when you have these k-mus acting on them. You don't get some magic appearing. So I want to say that k-mu on a primary operator is just whatever it is. It's this vector field psi mu nu d nu. On the operator, then there's 2 x mu delta on the operator. And if this operator has indices, we haven't done it, but as it happens in, if you work out all the details, you get, there's an extra term here, minus 2 x mu s mu nu I j. Well, S mu nu acting on the operator. So if this has indices, I'm not going to write them explicitly because then I have to insert a delta ij here. But think of this as some representation of the rotation group, rotation algebra. Again, if it's a fermion, it might be double cover and so on. Rotation algebra, then these are the matrices implementing that representation. So this is my definition of a primary. There's nothing else happening. And the only thing that can happen if an operator is not a primary is if it's a derivative of another operator, or linear combinations of more complicated things. But roughly speaking, there's a distinction in terms of primaries and derivatives. Descendants are derivatives of primaries. So we'll have a primary O of x, and then we act with one derivative, we get the first descendant. And then we act with 2 derivatives, we get the second derivative, we get the second descendant. And you see, so this is a scalar, say, then this is a vector. This is both a symmetric tensor and, of course, again, if I contract the indices, there are 2 representations of the rotation group, and so on. So these descendants have a more complicated action of k, which is annoying, but fortunately, they're just derivatives, right? So these are the interesting ones. Because suppose someone gives me all the correlation functions of all the primary operators, then to get these guys, I just take derivatives, which again, something that your sister that we talked about before can do, right? So these are the boring ones. to some extent. And so that's why I didn't bother with computing this number, because in some sense, who cares? I'll just stick to primaries. And then if you want to know correlation function of descendants, I'll ask your system. So so that's the nice and important classification of operators in conformal field theories. And notice that the primary, if it has dimension delta, then the first descendant has dimension delta plus 1. This has scaling dimension delta plus 2, and so on. So there are these towers of operators in conformal field theories. You have primary, and then there's a huge tower below it of infinitely many possible descendants.
Primary fields have a dimension, a well-defined dimension delta.
Yes, so this is what I'm getting to now. Let me state that explicitly. So delta is basically the action of the dilatation operator, or the scaling operator, when you insert the operator at the origin. DO0 is this delta. So what about these deltas? We're back to the original question, right? Are they real? Is this matrix is this matrix? These are the delta tildes in the Collins-Munzig discussion, right? Are they real? Is the matrix diagonalizable in the first place, and so on? So the answer is that in a unitary conformal field theory they are. So in a reflection positive CFT, delta are real. The deltas are also bounded from below, because delta, they're definitely greater than 0, because O of x of 0 was like 1 over x to the 2 delta, if I take two identical operators. So if these deltas were negative, then this thing would blow up, which would be a complete violation of cluster decomposition. So they're definitely positive, or non-negative. There's one operator with dimension 0, which is boring. It's just the identity operator. And often form discrete set. So this is true. It follows, for example, from the fact that the fact that the dilatation operator it generates rescalings, but there's this map from the plane to the cylinder, which tells you that the dilatation operator is also Hamiltonian for the conformal field theory on a cylinder, and then this is called radial quantization. And that's what you have to learn. If the dilatation operator is a Hamiltonian in a reflection positive quantum field theory, it better have real spectrum bounded from below. So that is one. So to understand all the words I said, I didn't want to spend time on this because I want to get to other things. To understand all that, you have to look up radial quantization. You can also ask me afterwards about what this means. But it's a bit of a detour that I don't really need. And operators, all the local operators are either linear combinations. If you do something silly, but they're either primary or descendants. Which is also something. So this is explained very well in lectures by David Simmons-Duffin. TASI lecture notes, I think from 2015 or 2016. Okay? Yes?
If you were to give me any given operation, how do I know if it is primary, descendants, and etc.?
No, I put it at the operator, right? If you, this is too abstract a question. I just put it at the origin, I see what KMU does. So that's one way. This is my definition of primary. And so in general, what you'll find is that it's a linear combination of primaries and descendants because you've done something silly and you just give a random combination of operators. But the dilatation operator is diagonalizable, so you restrict to eigenvalues, eigenvectors of the dilatation operator. And then you say, well, I have a discrete set, so there are only finitely many primaries above with a smaller dimension. Like there are only finitely many primaries that I have descendants of at this dimension. So you just do something like Gram-Schmidt. You have a reflection positive CFT, you have a good or inner product, so you just subtract away all descendants, and then what's left must be either 0 or a primary. Yes, I know. That's a good hint. Almost out of time. Okay, so let's write down then the correlation functions of primaries and descendants. Is everything clear so far? Any more questions? No? So we want to know correlation functions of primaries. Let's restrict ourselves to scalars for simplicity. So we need to solve, right? So let's look at 2-point functions. O1, x1, O2, x2. I told you this is C12 over x1 minus x2 to the delta 1 plus delta 2 over 2. So this takes care of rotations, translations, and scaling. But we also need to know KO1 x1. We also want this to be K mu to be 0. So these are no so this is actually true for primaries and descendant scalars, right? Because this is just rotation scalings. There was nothing but with K. But let's look at what extra condition we get for primary operators. I give them a little p because they're primary. Yeah. Sorry, yeah, there's no 1/2. Thank you. So how do we check the action? Well, we have some differential operator. We can just try to see how that works. There's a cleaner way, and it'll help us a lot, is just to exponentiate this. Let's do a finite conformal transformation. So there's a claim, and I'm not going to prove it. A finite special conformal transformation with parameter b is just x prime equals x prime is some function of x. That's a finite conformal transformation. That function is going to be I of x b and then I, or I p b, where I of x is just x mu over x squared. So it's like an inversion. That's why I called it I. It sends the point at 0 to infinity and the point at infinity to 0. It's easy if you know stereographic projection, the one-point compactification on the plane to a sphere, then it's relatively easy to think about, but it's a bit, so that's the thing you need to learn if you want to visualize this. I'm not going to say much about the intuition between this. B is just a translation. PB of x equals x plus b. So it's a vector b mu. So what you have to do, you just invert, you do a translation. So the point, it's like a translation in itself on the plane keeps the point at infinity fixed. It moves every point except the point at infinity. So what we do now is we just invert. We swap 0 and infinity, we do a translation, and then we invert back. So it's the kind of opposite of in the stereographic projection language is a translation where you swap the north and the south pole. It's like, so it keeps not the point at infinity fixed, but it keeps the origin fixed. And indeed, you see that the vector field psi mu, I erased it, I think, but the vector field vanishes at the origin. So it keeps the origin fixed. So this is a nice way to do, to check conformal, to check invariance under special conformal transformations. Because we can just say, well, let's just restrict ourselves to inversions. The translations will work. So let's just restrict myself to inversions, do the inversions, check that everything works under inversions. If it works under translations, rotations, and scaling, and inversions, then I get special conformal transformations. So in practice, that's a good way to check. I should also extend the claim. What should happen under an inversion for the correlation function, as I want to say the quantum version of this thing? Well, there's extra terms. So what this gives, if you do the maths, is that the correlation function should not be invariant. It should be covariant, like under scalings. And this is the transformation rule of the correlation function under inversions. So, for example, x1 minus x2 squared under an inversion goes to, well, this is has nothing to do with correlation functions. This is just a function, but you can easily check that this goes to x1 minus x2 squared over x1 squared, x2 squared. So let's check then our two-point function of primaries. We want that it's killed by a special conformal transformation, but really we want to check this property of the two-point function. So how do we? So we can check it now very easily under an inversion. You can check that O1 x1 over x1 squared, O2 over x2 squared. So this should be, by that rule, x1 to the 2 delta 1, x2 to the 2 delta 2. And then we'll plug in the original value. So this is C12 x1 plus x2 to the delta 1 plus delta 2. But of course, if we just do the inversion on the function that we have, we get that this is C12 over x12 x1 minus x2. x1 minus x2 to the power x1, we have x1 minus x2 squared to the power delta 1 plus delta 2 over 2. Right, so we get the same thing back, delta 1 plus delta 2. And then we get x1 to the power delta 1 plus delta 2. and x2 to the power delta 1 plus delta 2. So we have a problem. The form I wrote is not quite the form I'm supposed to get, unless, of course, delta 1 is equal to delta 2. So we see that C12 is 0 unless delta 1 equals delta 2. And if delta 1 is delta 2, if you have a bunch of operators with the same scaling dimension, then C12 is some symmetric matrix, but I can always diagonalize that matrix. So we're going to pick an operator basis. Pick a basis of primaries. Such that OI of x, OJ of y equals delta ij. We'll just make the nice unit norm and x1 minus x2 to delta. This is what I... So let me then... So we can repeat, of course, this exercise. We can repeat it for 1-point functions, for 3-point functions, for 5-point functions, and 4-point functions, and so on. So let me just say, we have this as a result. Let me just say the 1-point function, O of x. Well, by translations and rotations, it can only be a constant, but there is no dimensionful constant. In other words, or alternatively, you can say, under dilatations, this thing should be killed by dilatations, but that just multiplies the 1-point function with delta. And if delta is not 0, then this thing should be 0. So the only way this can happen is that this is 0 if delta is not 0. And then there's only one operator with delta equals 0 in reflection positive theories. That's the unit operator, and it has constant 1-point function. It has dimension 0. So those are the 1-point functions, 2-point functions we've done, at least for scalars. For 3-point functions, and this is the homework if you want to do something in this field. So let's solve rotations and translations and scaling. So it's only going to depend on x12, x13, and x23, the differences of these things. So we'll just take out all the scalings, x12 to the power delta 1 plus delta 2 plus delta 3. x12 is short for x1 minus 2. So that takes care of the scaling, and then we can have some arbitrary function which should depend on scale invariant combinations. So it can be x12 over x13, for example, or x13 over x23. So those are good combinations. So now we've done almost everything except the special conformal. So how do we solve special conformal? Well, a good way to try to see what you can get is to do something like this. So this is, of course, because I know the answer. So we'll just try to see if we can do some kind of power series expansion of this. So let me check which power I have in my notes. For those who actually want to try this, 1, 2 over 2, 3. And 1, 3 over 2, 3. So let me call this to the power alpha, this to the power beta, and then with some undetermined coefficient, g alpha beta. So as you'll find, not every value of alpha and beta is allowed. And so, in fact, you can check. So to do, check inversion covariance. And you'll find, of course, as many of you know, you'll find that this 3-point function is in fact very strongly constrained. And if you're brave, you can look at 4-point functions. There, it's a bit more complicated. but that is definitely something I should say for the next lecture. Any questions? No? Okay, then I guess I'll see you tomorrow. Thanks.
Right, this afternoon.
This afternoon?